In this video, we're going to talk about characteristic tests for carbonyl compounds, including 2,4-DNPH or 2,4-DNP, and Tollens reagent, and then go on to look at some exam-style questions. We'll also nip into the lab to show you what this reaction looks like in the lab, because you will probably be doing it for one of your assessments in the laboratory. So, identifying aldehydes or ketones with 2,4-DNP. You can identify an aldehyde and a ketone, but you cannot differentiate between the aldehyde or the ketone. You just know that there is an aldehyde or ketone present if you get a positive test with 2,4-DNP. It identifies the carbonyl groups within those functional groups, and you can see here there's a carbonyl group, okay, and this is an aldehyde because there is a H coming off that carbonyl group. We then have the ketone. You can see there's two R groups here, which are alkyl groups, and then we've got this carbonyl again. Something to note again, carbonyl is not a functional group, so it's not a functional group, so make sure you never put carbonyl down as a functional group in your exam. So, as I've said, you can call it 2,4-DNP or 2,4-DNPH, and that stands for 2,4-dinitrophenyl hydrazine. Again, don't need to remember the really long name, 2,4-DNP or 2,4-DNPH. It's perfectly fine. And it reacts with that carbonyl group, and it creates an orange or yellow precipitate. So here is a picture of our orange or yellow precipitate taken out of one of our labs. You can see here there is an orange solution, and then you've got this orange precipitate, kind of slightly yellowy precipitate at the bottom. And that's your precipitate that will be produced as a result of reacting with an aldehyde or a ketone. So that orange or yellow precipitate is your positive result. Now remember, aldehyde or ketone only, and you cannot differentiate between the aldehyde or the ketone. You just know you have an aldehyde or a ketone with this test alone. Now the 2,4-DNP looks like this. Do not worry, you do not have to remember this entire structure, okay, but it has appeared in exam papers before, and they've given it to the students within that question. So we thought it might be useful just to show you at least what it looks like and how it works. So this 2,4-DNP reacts with the ketone, and this carbon here will react with this nitrogen here. So as I said, that carbon, okay, is that carbon over there. So this carbon is that carbon there. And you can see that we have lost two hydrogens and we've lost an oxygen. Because we've lost two hydrogens and an oxygen, okay, we make H2O as our other product. Now I'd like to take you now through to the lab, and I'll show you how you actually do this reaction in the laboratory. In this video, we're going to talk through the reaction of a compound containing a carbonyl group with 2,4-DNPH. 2,4-DNPH also stands for 2,4-dinitrophenyl hydrazine, and do not worry, you do not need to remember that word or that name. You just need to remember 2,4-DNP or 2,4-DNPH. Now 2,4-DNPH is in this boiling tube here. So you can see it's a very orange colour, unmistakable, okay? And we're going to add it to a ketone. So when I say carbonyl, precisely, this is a test for a carbonyl that occurs in a ketone or an aldehyde. So we've chosen a ketone to put in this boiling tube, and that is butanone. And we've also put in the other two reagents, which is methanol and sulfuric acid. And together this is known as Brady's reagent. All you then do is take the two samples and then you add them together. You see straight away that the precipitate is produced, okay, and you have this orange kind of precipitate. Remember, it can also be yellow depending on what it is, and you have that precipitate produced. It proves you have a carbonyl inside your molecule. So what we can do now is we have to recrystallize this sample to turn it into a more purer sample. We're now going to do recrystallization. So you have to describe this in your exams, so it's really important you understand. So here we have our 2,4-DNPH derivative. This is the ketone or aldehyde that has reacted with your 2,4-DNPH. And we're going to take this precipitate and we are going to dissolve it in a minimum amount of hot solvent. So we have a recently boiled kettle right here, and we have our solvent in the boiling tube in here. You've got to make sure that it's very, very hot, so make sure that is a recently boiled kettle, okay, and make sure that you have enough solvent to do the recrystallization. Now normally you would add a minimum amount of hot solvent to make sure that your product crystallizes out at the end. So that minimum amount of hot solvent is really, really important. But for this video, we've measured out the exact amount of solvent that we need. So that's why we're just going to add all of this in here. So what we're going to do is take the hot solvent and then pour it into this derivative. So now we're going to put it into that freshly boiled hot water, and we're going to make sure we stir it. It's going to take a little bit just to warm up. And as we stir it, what should happen is the product will dissolve, and it will dissolve last because it doesn't dissolve very well in the solvent, but the impurities must dissolve really, really quickly and will dissolve really, really quickly. And now you can see that that's fully dissolved because of this hot solvent. All we have to do now is put it straight into the ice bath. This should happen almost straight away. And you put it straight into the ice bath, and that should mean that the product will recrystallize out and the impurities will stay in the solvent. And you can see that here, you can see it's falling. You can see this solid material falling to the bottom of the boiling tube. So we have our recrystallized pure solid with our impurities in the liquid, and we're going to perform filtration. So filtration is done via a vacuum trap which is attached to a water tap. Okay, and we have a Buckner flask, which is the bottom here, and a Buckner funnel, which is here. Then I have a filter paper on top, and what students mostly get wrong when they're doing this is they pour it in too quickly and then the solids go around the edge of the paper. So what you've got to do is pour it slowly and pour it down the center. And what should happen is it will be sucked through by the vacuum, okay, and you will start to get your orange precipitate which will form on the paper. Okay, and all you have to do is once you have filtered this, you leave it to dry for a day or so, usually in the fume cupboard at your school, and then you can perform a melting point analysis to identify what the actual ketone was in the first place. We're now at the last stage where we identify our 2,4-DNPH derivative. And then we can know what the ketone or the aldehyde was at the start, because there is a database online which shows you the exact melting point of derivatives of different aldehydes and ketones with 2,4-DNPH. Now we have our product here, and you can see our product of our nice orange precipitate. And that orange precipitate can be loaded into a melting point tube. So a melting point tube, bit of glass that's sealed at one end and open at another. And you take the open end and you literally just hit it into the solid, and so it goes into the tube. So you probably see that there, you can see here that is in the tube. And then all I do is take that, turn it the other way, so the sealed end is here, and then just start hitting it on the table. And I hit that very, very gently, and as I keep doing that, the solid falls down the tube and then ends up in the end of the tube. And as with a kind of Blue Peter moment, okay, you have got a pre-prepared tube here which has your solid in the bottom. All you do is then take that, put it into your melting point device, and lots of schools have devices like this, and then you set it to around about the temperature which you feel that it's going to melt. Now all we do now is look at the window, and as we look in the window we'll then see what it looks like when the 2,4-DNPH derivative melts, and we'll monitor the temperature. So now we've gone through all the stages of doing a 2,4-DNPH and using that to identify a ketone or an aldehyde. Okay, so the stages are, just to go over again, recrystallization, you then filter, And then after that, you will take the melting point and compare it to a database of known melting points of 2,4-DNPH derivatives. And we're now going to go back to the studio so that we can put that in the form of an exam question. Now we're back in the studio, we can talk through what you've done in the lab, what you've seen in the lab, and talk it through in a style of an exam style answer. Now each 2,4-DNP derivative has a specific melting point, but you must purify it first. Really important, you purify it first. Now to do that purification, you're going to use recrystallization as we did in the laboratory, and that separates it and allows you to do that through filtering. But let's go through the different parts of recrystallization in an exam style answer. So you recrystallize first, and I'd stop, if I was you, I'd stop the video, try and see if you can write this out before I've done it. Okay, you dissolve in a minimum amount of hot solvent, that's the first thing. Okay, that dissolves all of your product and all of your impurities. But your product doesn't dissolve in it very well. That's why you chose that solvent. You then reduce the temperature, and because the product doesn't dissolve very well, it then recrystallizes out, comes out, and you saw that orange precipitate coming out in the laboratory. Then you filter, and then the added bit is that you wash with cold solvent. The cold solvent, because it's cold, doesn't really dissolve the product, and so that gets rid of all the impurities that might be left on the product. And then you leave to dry in the fume cupboard overnight. Now, after you've done that, you've got a nice pure product which you can measure the melting point of and then compare to a melting point database of 2,4-DNP derivatives. And that means you can actually identify the original compound, the aldehyde or the ketone. Now there's two ways in which you can use 2,4-DNP. One of them is to identify the compound using this database. The other one is just to differentiate compounds. So for example, one has a carbonyl and one doesn't have a carbonyl. Well, 2,4-DNP will give you an orange-yellow precipitate when there is a carbonyl and no orange-yellow precipitate when there is not. So it's a way to differentiate and a way to identify, depending on whether you use all of this answer or just say that it has an orange-yellow precipitate. But now we're going to move on to the next identification reaction, this time for aldehydes or ketones. Let's now go and look at the next test, which is Tollens reagent. This allows you to test for aldehydes, and therefore you can tell the difference between a ketone and an aldehyde, because a ketone will not show a positive result for this test, but an aldehyde will. So aldehydes are oxidized by Tollens reagent and they produce a silver mirror effect, and that's an exam answer. Okay, so if you put a silver mirror is produced, that will get you a mark. The next thing is the silver plus within the Tollens reagent is the oxidizing species, and it's usually called ammoniacal silver nitrate. But ammoniacal silver nitrate is not really required for the exam, just call it Tollens reagent. Now the Tollens reagent includes this Ag+, you add an electron to it to get Ag solid. The Ag solid is your silver mirror, okay, and therefore the Ag+ is reduced. And therefore if it's reduced, it is the oxidizing species, so it's the oxidizing agent. Now we have to go through an exam tip now, and the exam tip is really important for those higher marks and ones that normally are missed by students. It will only oxidize aldehydes, so do not oxidize the alcohols in a structure if you're using Tollens. So often people think because it's an oxidizing agent, it will just oxidize everything. It doesn't oxidize the alcohols because it is not a strong enough oxidizing agent. So just the aldehydes, not the alcohols. Let's look at an example. So we've got an alcohol here, we've got an aldehyde here. We then add an oxidizing agent, and that oxidizing agent is Tollens, and you can represent it as O. Okay, and then look at our product. Our product is a carboxylic acid, and the alcohol stayed the same, exactly the same. So it's only this aldehyde here that has turned into this carboxylic acid here. So only change the aldehyde, do not change the alcohols. Now what does this actually look like, this oxidation? This oxidation looks like this. So normally in the actual, in the laboratory, you will do it and then add this to an aldehyde and you'll get this beautiful silver mirror on the inside of a boiling tube, and sometimes they allow you to take that home. And if that's what you get if you've got an aldehyde. If you have a ketone, it just stays a brown, horrible mess, and it's not very pretty. Okay, so the silver mirror is your positive result if you have an aldehyde. We're now going to pull this into an exam-style question on qualitative analysis, and this is basically when you have got chemical tests done within the laboratory, colour changes and etc. and stuff like that, and you have to identify and distinguish between different functional groups. So the question normally is written like this: describe the positive chemical test to confirm the identity and distinguish between the following compounds. If you're confirming the identity, you have to do a test to make sure you know what something is. Distinguish, you just have to make sure you do enough tests to prove that they're not the same as each other. But it says confirm the identity in this question, so we have to do enough tests to know exactly what everything is if we're given some options. So let's move that to the side and then give you our compounds. So the compounds are usually given in structural formula. Okay, and what you have to do is do 3 different parts. So you have to identify the functional groups, then you do the test and say what the test is, and then you will do the positive identification of that test for that functional group. So let's start to do it. I like to put this in a nice, neat table. So there we go. And then I want to look at each one in turn. So first of all, I've got an OH, which is an alcohol, and it's in the centre of a chain. It's got 2 groups either side of it, therefore, and it's got 1 H, therefore it's a secondary alcohol. I then look at this one, CHO. CHO signals to me I have an aldehyde. Now, let's go on to the next one. I've got a repeated secondary alcohol here. And then I go to the last one, and I've got the CO here. And hopefully, if you see CO like this, with 2 R groups either side, that is a ketone. So we've got our functional groups, and we've identified all of our functional groups. Remember, you can stop the video and you can do this question without me and then get me to explain. So let's go through the tests now. So if I'm looking for an aldehyde and to differentiate this from this from this, the aldehyde is going to react to a Tollens. And if it does react to a Tollens, it's going to create a silver mirror. And therefore I will get my marks for that because I've identified it, because it's the only aldehyde in there, and therefore I've now identified it. We then go for the secondary alcohol. Now what do we do with a secondary alcohol? We can oxidize a secondary alcohol, okay, because we've already differentiated the aldehyde, so we know that that's the aldehyde, so we can forget that. So it doesn't matter that this is a secondary alcohol and this is, because I've already decided that's the aldehyde. I want to differentiate now this alcohol from this ketone. So if I put in H plus Cr2O7 2-, or the oxidizing agent, that is acidified potassium dichromate, this will turn into a ketone. Now think, what is the colour change there? Well, the colour change is to take it from orange to green. So I've got a positive colour change, and so I know. So unless you can see a colour change, or bubbles, for example, you can't identify this. So we've got nice orange to green. Now, also, things not reacting can be a sign of what they are. So if I put H plus Cr2O7 with this, there'll be no colour change and it will stay orange. So I've now identified and distinguished between those 3 molecules. And this is a very common style of question to ask, in which they'll put 3, 4, 5, sometimes even 6 different molecules in front of you and ask you to write out how to differentiate or identify them. And I do really recommend identify the functional group, identify the test, and say what the positive identification is.